Good morning, good afternoon, good evening, depending where you're joining us from. My name is Kirsten Stephens, and I'm a fifth-year PhD student at Penn State University, working with Dr. Christelle Wauthier. And today I'd like to talk to you about some of the research I've been doing at Masaya Caldera using radar satellite datasets to look at ground deformation during different periods of volcanic activity. And the background image shown here is a beautiful lava lake that formed in December 2015 at Masaya at the summit, and is currently persisting to this day. So if we take a little bit of a step back and have a look at some of the kind of key questions in volcanology, what I've shown here is the classic cross-section of Kilauea's magma plumbing system as an example. And we've got a number of different magma reservoirs located in the system at the summit, as well as along the different rift zones. And then we've also got these different rift zones leading from those reservoirs, creating this magma plumbing system. And as we learned in the 2018 period of activity at Kilauea, is that it's really important to know how and where magma is being transported, as well as where and how long that magma is being stored in different locations. And in the geodetic community, it's really important to look spatially and temporally at ground deformation patterns to get at what's happening in the magma plumbing system during these different periods of volcanic activity. And so this leads to my main objective of my research is to understand how changes within the magma plumbing system influences ground deformation and volcanic activity in order to improve forecasting and mitigation of volcanic hazards, and in particular for caldera systems. So to get at this, I've been using the Interferometric Synthetic Aperture Radar, or InSAR approach, which is an active remote sensing technique used to detect ground deformation. And so if we subtract the phase between two SAW images, we get to look at the ground deformation between these two acquisition dates. And if we have some form of deformation event occurring between these two dates, we expect to see this captured in our deformation maps. And I will be talking a lot about line of sight, or LOS, throughout the talk, and that's just simply has to do with the oblique viewing geometry of radar satellites. And this incorporates both vertical and horizontal components of the ground deformation. Masaya is a caldera located in Nicaragua and forms part of the Central American volcanic arc, and is located about 20 kilometers to the southeast of Managua City, which is the capital. And over its lifespan, Masaya has exhibited a wide range of volcanic activity. And this has ranged from effusive lava flows and lava lakes to explosive small throat-clearing events to phreatomagmatic and Plinian eruptions that have formed the caldera we know it today. Because Masaya exhibits these two different end members of activity, it's really important to get at the behavior of the system to determine perhaps when one type of activity will be preferred over another. So if we focus into the caldera itself, which is outlined here in black, we have our summit, which consists of a number of nested pit craters, and we also have a semicircular ring of previous vents within the system. And in particular, the Santiago pit crater has been the most active recently, and this is hosted and is currently hosting the 2015 lava lake. And only a handful of InSAR studies have been made at Masaya, and only a few of them, of these few, have been used to look at the magma plumbing system and do geodetic modeling. So if we take a cross-section from just to the south of the summit up to the north through the caldera itself, we can have a look at some of these results. And so the green model that is shown up at the summit, very shallow part of the system, looking at a period of time where we saw sub-centimeter deformation associated with the 2012 explosive period of activity at Masaya. And the red sphere that we're looking at over here is a preferred model which spanned the period of the appearance of the lava lake at the summit. And so this particular reservoir, this spherical reservoir, is actually located 3 kilometers to the north of the system and has extended our current knowledge of the extent of the magma plumbing system at Masaya. And so the fact that we're observing two different locations of the magma plumbing system being kind of lit up in terms of ground deformation during different types of volcanic activity, I wanted to get at understanding a little bit further if this is a consistent thing or if we're also seeing different parts of the system also being lit up during different periods of activity. So I extended the study to look at the last 10 years at Masaya. And so you can see there's periods of incandescence, seismicity, explosive eruptions, as well as, of course, our lava lake period. So what I'm showing over here is just the number of data sets that I've been using to look at this period at Masaya. And so we have a number of Sentinel-1 ascending and descending pods and frames, as well as Cosmos SkyMed and RadarSat-2, which have been kindly provided by the CEOS Volcano demonstrator. But for this particular talk, I'm going to just focus in on some InSAR time series results between 2015 to the end of 2019. And so this has been processed using the small baseline subset approach. And so the data sets that are being shown here is simply each color is representing each of those different SAR data sets I showed on the previous slide. And all of the data sets have been shifted in order to correlate with the Cosmos SkyMed, shown in red here, time series, so that we are able to compare the patterns of the deformation. And these are being plotted up over the maximum center of line of sight displacement during these lava lake periods of activity. And so what we see prior to the appearance of the lava lake is that we have a slight to minimal increase in line of sight displacement. And then about 6 weeks before the appearance of the lava lake at the summit, we see this region beginning to inflate a lot more rapidly until reaching a peak in line of sight displacement about 10 months into lava lake activity. And then slowly and steadily over time, we start seeing this decrease in line of sight displacement. And so what's really great is we're seeing similar patterns for all of these different data sets, which have different ascending and descending orbits. But of course, because of these different viewing angles, we also have some slight discrepancies in terms of line of sight displacement. So for example, RadarSat-2 here perhaps is under predicting the line of sight displacement, whereas the Sentinel-1 ascending data set may be over predicting it. So if I combine the Cosmos SkyMed time series with gas geochemistry results, so carbon dioxide, sulfur dioxide results, as well as some volcano radiative power results obtained through the Moreover project, we see some just very interesting initial observations. And so Ayupa and others postulated that this peak in carbon dioxide, sulfur dioxide prior to the appearance of the lava lake was affiliated with the intrusion of magma from depth. So carbon dioxide rich magma coming into the system from depth, and this resulted in the appearance of the lava lake up at the summit. And when we look at comparing the thermal with the InSAR data sets, what we observe is that the peak in the thermal is roughly around the same period of time where we see this peak in the line of sight displacement from the InSAR. And we see that over time, we have a decrease in our thermal as well as decrease in our line of sight displacement results. And visual observations made of the lava lake itself suggested that over time, lava lake activity has been less vigorous. And so in conjunction with our InSAR and the thermal, it's perhaps that we have a slight depressurizing of the system as a whole, and thus less lava lake activity at the summit. And so just to summarize some of these key results, so preliminary results are suggesting this increase in line of sight displacement prior to the appearance of lava lake, reaching a peak in line of sight displacement after the first 10 months, and then decreasing over time as lava lake activity continues. And comparing this with our gas geochemistry and volcano radiative power results over time, as well as visual observations, this is then suggesting we now have potential depressurization of the system. And so I'd like to investigate this further by using the multidimensional SBAS approach, which allows me to ingest all of my different data sets and to get at the nitty-gritty of the vertical and horizontal components of the ground deformation we're observing. And on top of that, using those different results to perform some geodetic modeling, and also then use, for example, the gas geochemistry results to then validate some of the modeling results we're getting out. So thank you so much for your attention, and I'm happy to answer any questions that you have.